Good morning. In this video we are going to discuss the topic double integration method. So it's a direct method. By means of using the direct formulas we can easily identify the slope and deflection of a beam when it is subjected to the external load. Based on the support conditions and nature of load acting, we can easily find out the slope and deflection by direct formulas. Here I would like to discuss some type of support conditions and their loading. First one, when the cantilever beam is subjected to point load at its free, the maximum deflection is occur at the free end of the cantilever beam. See here, the cantilever beam is subjected to a point load at its free end. Let L be the length of the cantilever beam and W is the load acting on the beam. So the maximum deflection is always occur at the free end of the beam, and the deflection is corresponding to the center portion we can calculate by the formula, and the slope is occur in between the length. So in these conditions the maximum bending moment value will be calculated by the formula load into distance. Here W is the load and L is the total distance. The negative sign indicates the deflection, the maximum bending moment will be occur in the downward direction, so that in all cases we are just mention the sign minus. Next one, slope. The slope at point B will be equal to minus WL cube divided by 2EI. By using this formula we can easily find out the slope of the beam at point B. Next, maximum deflection. Maximum deflection of a cantilever beam subjected to point load at its free end, the maximum deflection is minus WL cube divided by 3EI, where EI are the flexural rigidity. By knowing the value of Young's modulus and moment of inertia and the load acting on the beam and the total length of the beam, we can easily calculate the maximum deflection occurring in this type of beams. And the second condition, in a cantilever beam, a point load of capital W is acting at a distance of A meter from A and B meter from end B. In this case, we have to calculate the maximum bending moment, slope and maximum deflection. The formula for maximum bending moment is given by minus load into distance. This distance is always based on the fixed end distance. So here we calculate MA is equal to minus W into A. It is clear that in cantilever beam only we are having the bending moment, so that we have to calculate the bending moment only in the point A. So MA is equal to load into distance. So load into that load W is acting from A meter distance, so minus W into A. Second one, slope theta B is equal to minus WA square divided by 2EI. Maximum deflection Y max is equal to minus WA square divided by 6EI into 3L minus A, where L is the total length of the cantilever beam and A is the length from the support. Next case, when a cantilever beam is subjected to an uniformly distributed load throughout its length. Consider here total length of the beam is L and UDL load of intensity small w per unit meter is acting throughout the length of the beam. In this condition also the maximum deflection will be occurred at the free end only, and the slope at B can be calculated by the given formulas. Maximum moment MA is equal to minus WL square by 12 or minus WL divided by 2. The only difference is if we are going to substitute the load in point load, means we have to use the formula minus WL by 2. Or else when we are using the UDL load itself, then we can use the formula minus WL square divided by 2. In order to convert the UDL load into point load, we have to multiply this point load into distance. So the formula becomes capital W is equal to small w into L. Slope for this condition will be equal to theta b is equal to minus WL cube divided by 6EI, or we can use the another formula WL square divided by 6EA. This is nothing but WL into L, so it will become WL cube, or we can use the formula as WL square divided by 6EA. The maximum deflection will be equal to minus WL power 4 divided by 6EA, or minus WL cube divided by 8EA. Either we can use the formula itself, which means directly with the unit load, or we can use the point load also. UDL load or point load, both we can use, but the only difference is we have to change the formula according to the usage. Next one, in this condition, a cantilever beam of length L is subjected to point load and UDL load for B meter distance. At a distance A meter from the fixed support A, there is no load on it. After that, up to the full distance, UDL load of W Newton per meter is acting. In this case, the maximum bending moment value is given by minus W into L minus A into L minus A divided by 2 plus A. Slope of the beam is given by theta b is equal to minus W divided by 6EA into L cube minus A cube, where L is the total length of the beam and A is the unsupported length of the beam, and Y max is given by minus W divided by 24EA into X into 8L power 4 minus 4L A cube plus A power 4. Next type, when a simply supported beam subjected to a point load at its center. Consider here the total length of the beam is L and the load W is acting at the center. So equal distance L by 2 and L by 2. In this simply supported beam, there will be two support at A and B, namely A and B there are two supports, so that the slope will be formed at two ends. One is theta A and another one is theta B. For that we have to calculate both the slopes, both the supports we have to calculate the slope value, and also the maximum deflection is always occur at the middle portion of the beam only. So maximum bending moment is given by the formula WL by 4, and the slope at A, which is equal to minus WL square divided by 16EI, and theta B is equal to plus WL square divided by 16EA. One side it is negative and another side it is positive. The maximum deflection will be given by Y max is equal to minus WL cube divided by 48EA. When the simply supported beam having point load at its center, the maximum deflection is always minus WL cube divided by 48EA. And second case, simply supported beam having point load at its unequal distance. Here from support A, from A meter distance and from support B meter distance, the W load is acting in the simply supported beam. So in this case we have to calculate the maximum deflection somewhere between A and B. So at what place the maximum deflection will occur is the important one. So in order to calculate this, we have to calculate both the support moments and the slopes. In simply supported beams, both the support moments are always 0. So the maximum bending moment will occur in between the load. So the maximum bending moment value, which is equal to WAB by L, where W is the total load acting on the beam and AB are the distance corresponding to the load, and L is the total distance of the beam. Slope at A, which is equal to minus WB into L square minus B square divided by 6EA into L. Similarly, slope at support B is equal to plus WA into L square minus A square divided by 6EA into L. Here we have to calculate two moments, namely first moment is under the load. For example, if the load W is acting at a point C, means we have to calculate the load value, load and deflection values. So the deflection is under C, and also the maximum deflection will occur in between anywhere the support from A to C. So Y max, which is equal to minus WB into L square minus B square whole power 3 by 2 divided by 9 into root of 3 EA into L. The deflection under the concentrated point load C, YC is equal to WA square B square divided by 3 EA into L. Next condition, when a simply supported beam is subjected to UDL force throughout its length, means the maximum deflection is always occur at the center portion of the beam only. Similarly, here also we have to calculate both A and B slopes, slope at A and slope at B. The maximum bending moment is given by the formula M max is equal to WL square divided by 8, and the slope at A, which is equal to minus WL cube divided by 24 EI. Slope at B is equal to WL cube divided by 24 EI, and the maximum deflection is given by minus 5WL power 4 divided by 384 EI. By using these formulas, we can directly calculate the slope and deflection of the beam. First problem, a cantilever beam 1.5 meter long carries an uniformly distributed load over the entire length. Find the deflection at the free end if the slope at the free end is 1.5 degree. So, write down the given data. A cantilever beam is given and the UDL load is acting throughout the length of the beam. So, whose unit weight is W per meter length. So we know that the maximum deflection will occur always at the free end of the support. Length of the cantilever is 1.5 meter. So convert this 1.5 meter to mm, 1500 mm. Slope at the free end is given 1.5 degree. So in order to convert this 1.5 degree into radians, we have to multiply this by pi by 180. So deflection at the free end, we know that when the cantilever beam subjected to UDL load throughout the length, the formula is WL cube divided by 6 EA. Here we are not using that minus sign because it's just indicate the deflection is in the downward direction. So no need to substitute this minus sign in everywhere. So simply we can substitute WL cube divided by 6 EA, which is equal to, that slope is given by the problem 1.5 degree, that is equal to pi by 180 into 1.5. So equating these two, we can get WL cube divided by EI is equal to pi into 1.5 into 6 divided by 180. So from this we can calculate the value of YB. We know that the deflection at B, Y maximum is always at the free end. So the maximum deflection formula is given by the which is WL power 4 divided by 8 EI. By substituting this, we can rewrite the equation as WL cube into L divided by EI into 8. So WL cube divided by 3 EI, we know that WL cube divided by EI into 8. From the previous step, WL cube divided by EI value we already found, it is pi by 20. Instead of WL by L cube divided by EI, we have to substitute pi by 20 into 1.5 divided by 8. So the final answer becomes deflection under the point B, YB is equal to 29.45 mm. And next one, second problem, a girder of uniform section and constant depth is freely supported over a span of 3 meter. If the point load at the midspan is 30 kN and Ixx is equal to 15.614 into 10 to the power minus 6 meter power 4. Calculate. First one, central deflection. Second one, the slopes at the ends of the beam. Take Young's modulus is equal to 200 giganewton per meter square. Solution: total length of the beam is given, L is equal to 3 meter, and the point load which is acting on the beam at centrally, W is equal to 30 kilonewton. Moment of inertia in x direction, Ixx is given 15.614 into 10 to the power minus 6 meter power 4, and E value is also given 200 giganewton per meter square. We know that when the simply supported beam carries a point load at its center, the deflection maximum is given by WL cube divided by 48 EA, which is acting on the downward direction. So substitute this maximum deflection WL cube divided by 4 EI in the equation. W is here 30, so 30 kilonewton will be 30 into 10 to the power 3 Newton into length value is also given. Length value 3 meter. So substitute 3 meter, 30 into 10 to the power 3 into 3 cube divided by EI 48 EI, 48 into E value 200 giganewton. So 200 into 10 power 9 into I value is also given. Substitute all these values, we can get the value of maximum deflection as 5.4 mm. Slopes at the end of the beam. At end A, theta A, the formula is given minus WL square divided by 16 EI. So substitute the values minus, instead of W 30 into L square 3 square. So in order to convert this kilonewton into Newton, we have to multiply with 10 power 3. So the equation becomes minus 30 into 10 power 3 into 3 square divided by 16 into E into I. So substituting these values in both theta A and theta B, we have to calculate the final answers of slope at A as minus 0.309 degree, and also slope in the support B will be plus 0.309 degree. So if it is convenient, we have to calculate this value into radians also.